let's warm up this morning with a little bit of heat transport and a little bit of derivation. The yummiest part of this course, I'm sure, for most of you. So we are working on laminar flow, and this laminar flow is in our favorite geometry, that would be cylindrical tube. However, this time for a special perk, the tube is heated, and it's heated, of course, from the sides. So that wouldn't necessarily make sense to heat the tube only on inlet and outlet, and I'm not sure how would that be executed anyway. So the only way we can do is we can wrap up the tube. So this is something that is very much of application in any kind of pipeline systems, depending whether they're in a cold place or under the sea. So we often have to actually think about possibly heating up the oil, because oil, of course, flows easier if it's warmer. Even if it starts warm, oil often comes out of the ground rather warm, but it could cool off rather rapidly, and that causes all kinds of problems in terms of precipitation of various components from the oil itself, formation of hydrates, and so forth. So we might actually need to continuously warm up the pipe in order to ensure the flow. So what we're going to do here is we're going to assume knowledge of our velocity profile from the beginning of the course. And this is often how these problems are solved. They're sort of decoupled. Even when I actually have, so that means that we're not going to, for all intents and purposes, assume that this heat influx from the sides is changing anything about momentum transfer properties. So viscosity is not going to change as a result, though it might. So regardless of whether it does or it doesn't, you kind of, for the time being, you freeze and you assume the knowledge of your velocity profile or your momentum transport. You use that knowledge in solving for heat transport, or maybe you're coupling any other type of transport. It doesn't really matter. Sort of the conceptual procedure is the same. So you freeze one for the time being, assume you know it, and then you plug it into the other one, solve and advance that one, and if you need to, you update viscosity and you keep going. Okay. One simplification that we're using also here is that this tube has laminar flow, which that's a relatively small tube then. Pipelines can go anywhere from here to being something larger than myself, right? So anywhere in between there, it's a fair deal and fair span. So we're limiting ourselves to laminar situation here. Then in reality, we might have turbulent flow and need to solve for the flow profile accordingly. So let's get going. Essentially, what we need to be aware of are boundary conditions, always. So for the heat flux, I'm assuming, so it's a negative value of heat flux because I'm flowing opposite the radial direction. And I'm assuming that I know the temperature at the beginning of my pipe, and question is what it is along the pipe further down the road. This is the velocity profile, our standard parabolic velocity profile that I assume known, and I'm just going to write Vz max. It's a constant that I know from the pipe and fluid properties, times 1 minus r squared over r squared. Now I did go actually in this development a little further. Let me try to find once again, where did I save it? It should be this one. Yeah, this is the one where I stopped. So then we do our standard shell balance. This is our little cylindrical shell, okay? And what I'm balancing is my combined heat flux. When I write it in a pretty way, it's just E. But when I write the full glory of it, I have in there convective components. So there is basically internal energy hiding in this enthalpy piece, but enthalpy is also picking up PV from my molecular transport. And then we have shear stresses, work of the shear stresses, that's tau dot V, and the heat flux that is solely due to the temperature differences. This is how we break down our combined energy flux. So when I balance it in the tube, it's one sole vector, so I look at all of its components and the portions of it that are going in and out of different sides. So basically in the radial direction, I have the only component that is able to pass through is the one normal to the radial surface, and therefore that's ER. So ER times the appropriate area at R is equal to R, and then minus ER evaluated at R plus delta R and times the appropriate area. And for for Z direction, the same thing. The only thing that is getting into this little shell is the EZ component, and basically I have to multiply by appropriate areas to sum up the actual amount that is going in and out. And then we should not forget the work done by external forces. In this case, it is gravity. Okay? So I basically do a dot product with my velocity, and I get the following, because only Z direction for gravity is the one that is active. So once I actually put these areas in, I am going to get the following. So I am going to, my AR is 2PR delta Z. And then my AZ is approximately similarly in the development we had before. We ignored the second order term. So it's approximately 0 P times 2 R delta R. AZ is the same as a Z plus delta Z. It doesn't change, the area doesn't change in Z direction. So I would again divide that by volume. Okay, so this is volume of the element. And then I'm going to also recognize that I have here, this is ER evaluated at R times R, and then ER evaluated at R plus delta R times R plus delta R. The 2P part is going to disappear, delta Z as well, and that's basically divided by R delta R, right? So it's essentially minus 1 over R, R ER evaluated at R plus delta R, divided by delta R. Take a moment to agree with me. And Z part is easy. Z is easy. It's EZ evaluated as Z and Z plus delta Z divided by delta Z plus rho G VZ is equal to 0. Do we see the differential equation this is going to? We shrink now this shell. And we will get and when I shrink it, I will get the partial differential equation plus rho g vz is equal to 0. So this is what I'm solving. Looks very much alike like what we've been seeing for momentum transport. It's just that this E is deceptive because it's way different than we had in the momentum transport. So what is my ER? ER is the R component of that energy flux. So I have this part is scalar, but its R component is BR, right? Plus tau dot V, the R component is tau R VR plus tau R theta V theta plus tau R Z V Z. It's essentially, tau dot V is essentially multiplication of a matrix representing the stress tensor and the vector that is representing velocity. So I just go and look at the appropriate row. It's like, oh yeah, when I tell you that it is, then it's obvious. But when you see something like tau dot V, like our component is like, oh my God, what is that, right? So, well, the good news here is that VR is 0, yay. VR is 0, V theta is 0. So I have tau R Z V Z plus QR, and when I write that out, it is minus mu dVz dr Vz minus k dt dr. Yes? All right. So that is my ER. Let's take a look at easy. Is easy easy? Let's see. Sorry about cheesy jokes, but I can't help myself. Let's warm up with heat transport. The biggest advances in all of these, I guess that's going to be driven by movies, but it will help science as well, is that you will be able not only to do simulation of heat transport, but also feel it, right? So have some device that will heat up to the temperature you can simulate, assuming a reasonable range, of course. And the second one I want is like some sort of like simulation of smell, a proper simulation of smell when you have a movie, or if you smell and taste, like when you're watching a cooking show. It's like, I want to taste that thing. Can you simulate it, please? Okay, back to our easy. So this is my, So this is the z component. Then here I have the only one that is actually non-zero when I actually look at what I had before is tau z z v z, potentially. The other two are 0 because Vr and V theta are 0, and plus Qz. Now even here though, tau zz is essentially dvz dz minus 2 mu, and that is equal to 0. So that's going to go. So this component is not 0 though, so I do have to write down what everything is here. Plus rho h0 plus rho cp t minus t0 plus p minus p0 vz. This is, I'm writing what my rho h is, rho h hat is, based on what we read last time, plus qz. Well, actually, let's write down what qz is. Qz is minus k dt dz. Cool. So now I have to put it up in this equation. Yes.
Isn't the first term supposed to be just b squared?
Which one?
1/2 rho b squared?
B squared, yes. Well, yes, and Vr in V theta are 0. So yes, in this case. Okay, so let's put things in. So what I have is, I'm going back from here. Let me actually, this one is the easy is a pretty long term. So what I'm actually going to do is immediately take a look at if I do partial derivative of Ez, what's going to go to 0? So this term here will be, when I multiply it with Vz, it's going to be 1/2 rho Vz cubed. When I do a derivative with respect to Ez, this one is going to go, I'm going to just say goes to 0. Okay, just to shorten the writing a bit. This, the same, it's a constant times Vz, so this one will go to 0. Okay. This one not necessarily. Okay, so that's partial z of rho Cp t minus t0 Vz. And plus partial z and minus k d squared dt dz squared. And just to completely then derive it, so since partial z of Vz is equal to 0, then this comes down to rho Cp dt dz Vz. Yes? And in this term here, So that is dpdz times vt. And minus k dz squared. So if I put it in, here I'm now going back to my red equation, so maybe I can continue in red color just to be obvious. Derivations so far were sort of a helping hand. So I have minus 1 over r, and then my ER is all negative. So that's 1 over r ddr of mu r dvz drvz plus k r dt dr. Then minus dez dz, so I have that term right in front of me. And plus k. And let's not forget this last term, plus rho gvz is equal to 0. So one thing that we're going to eyeball here to simplify, since there are some elements that are similar to the equation of motion, I am going to break this down. Okay? And then because there's rho g here times vz, there will be partial derivative of this first time times vz, and then times this times partial derivative of vz part. So maybe I can kind of, and then dp dz times vz. So I'm going to break this down and isolate Vz to see whether I can recognize the equation of motion and cancel it out. Because there's a term there that should be 0, right? Add up all the parts. So that will simplify our development sum. But then there will be still plenty left, okay? This is a complex equation. So let's go towards that. And the only bad part about this software sketchbook that I'm using for this, it doesn't want two things open, so I can't have my old one in front of me. So you're gonna have to make sure I'm not making a mistake here. All right, so now we continue. Okay. So it's 1 over r ddr of mu r dvz dr vz plus 1 over r mu r dvz dr dvz dr. Everybody agrees with me? So I coupled mu r dvz dr, and vz is the rest. So then I had the partial derivative of that part first times vz, and then times this coupled portion times the partial derivative of vz. Plus 1 over r. I'm just going to keep this as is. And then we had the So that's my first term, and then my z term was so this is the TVZ part. I'm looking for. Oh, all of this is equal to 0. That part is this is essentially equation of motion for this cylindrical tube. So mu 1 over r mu r, so that's mu dr squared. Qr dt dr minus rho Cp dt dz dz plus q d squared dt dz squared is equal to 0. So this is what we are left with. I'm going to write it as follows. Rho Cp dt dz vz. I'm going to put that to be positive on left hand side is equal to, and then I have stuff that is multiplied by k, 1 over r d dr r dt dr plus d dz squared. So thanks to the simplification of equation of motion, I have a certain convective transport term here. Okay. This is my molecular heat transport. Okay. And this term is actually, it's a friction heating, and it's often rather small. Unless I'm in some sort of like, just like we had like the thin geometry in between, like annulus or something of that sort, where heating could actually be considerable. So the way this is often actually broken down, so just again, this is convective transport.
This is molecular transport. And this is often assumed small. And as is, this cannot be still, even when I ignore this part, I cannot solve analytically. What does help then is look at these components here. So I have second order derivative in T, first order derivative in T, and then this component. So this can be actually the equation without this. You're going to get it, but this is but it's essentially related to Laplace equation. So we can actually solve that, assuming Vz known and constant for the time being. So can we ignore this first offender here that bothers me is the second derivative in T? Well, so we have radial transport, and some of it also dissipating in z direction. So if I do assume that this heat influx from the side is dominating, okay, then in that sense, d squared dt dz squared, the dissipation in z will be relatively minor part. The z component transport will be dominated by convection with velocity vz. So when I compare basically these two and these two, this one loses in both types of comparison. So in my z direction, this type of convective transport is going to be most likely dominant. And then in r direction, I have the actual heating. So once that is done, then you can actually solve this analytically. So let me write that down. Even with dvz, dr assumed 0, we cannot solve analytically. However, convection in Z dominates over dissipation d squared dt dz squared. And molecular transport in R dominates in R. Good luck reading that. Not even I can. I'm like, what did I write? No, in R dominates d squared dt dz as well. And this is because of boundary conditions, right? Have we deciphered? This is how I wake you up. You gotta decipher what I wrote down. Otherwise, you would just fall asleep. So basically, assume, let me write that down. Assume dt dz squared is approximately 0. Once we do all of that, then I'm going to get, did I do this too quickly? Do you want me to do the page? Sorry. May I? Okay. So then what we're left with as a system is rho Cp Vz max 1 minus r square over r square dt dz is k 1 over r ddr and t is t1 at z is equal to 0. Qr is minus Q0 at r is equal to r. That basically gives me what dTdr should be at r is equal to r. And basically noting that t is finite at r is equal to 0. This then actually does have analytical solution. We are not going to go into finding it. But you can take a look at figure 10.83. So one key thing, other than mechanics of solving these things, is that you should be able, when you're given an equation, you should be able to recognize where the different terms coming from. So which one is convective transport, which one is molecular transport, which direction is obviously obvious often, right? But still, so that you know how to split basically different directions, right? And different types of transport, so you can analyze whether which part of it is dominant and which part of it can you actually live without. So that's one of the key things is like when you look at the, even if I've given you differential equation, right? Can you pick out what is coming from where? So that's something to practice as you kind of are solving problems. Okay. All right. We have 10 minutes. Good. So now we're actually just going to generalize this a little more. So this is basically, we're going to have one more problem, but this is problem solving for now. And we're just now going to formulate, well, what happens when I don't have steady state. Okay? So how does my entire equation look like? And it's just a shell balance, just like it was before. So in that sense, there will be no huge